All right, hello everyone. Welcome to another exciting adventure in interview preparation. Let's get started. So today we are going to, whoops, I'll go back here. Today we're going to talk about hash maps and heaps, which at least one of them is my favorite data structure. The other one I just sort of do whenever I have to. But yeah, so today we're going to talk about hash maps and heaps. And we're going to have a little time for you to practice. And yeah, that's going to be the session for the day. So if you have never seen one of these lectures before, or if you've never come to one of these before, or if you've never even done a technical interview before. So just to give you the scoop, technical interviews are a process that software engineers need to go through in order to demonstrate their engineering capabilities. So there's different formats that they can take. Often you'll have an online assessment. That's really the first round. Usually it's just an automated online assessment where you're given some problems and you have X amount of problems to solve in Y amount of time. There's also live coding assessments. These are usually your second or final round assessments where you are solving an algorithmic challenge in front of a staffer or someone on staff. And you work with them and you communicate with them as you solve the problem. And then finally, something that we don't really see anymore, thanks to COVID, is an in-person whiteboard interview where you're talking with a person on staff in person, and you have a whiteboard and you're drawing out the solution to your to the algorithmic challenge. So different formats, but all of them sort of get the same, or the purpose is basically the same. First, can you solve the algorithm, right? Can you even do the problem? Second, how efficient are you at solving the problem? Meaning, how much time does your algorithm use as n gets larger, or the input gets larger? How much space does your algorithm use as the input gets larger? And then if you're doing this in person, communication. I think sometimes people forget that we're hiring, or people are hiring for coworkers. You know, they want to be, they want a new member on their team. And so one of the things that you have to keep in mind is like, how well are you communicating? Do you take hints when they're given? When you're frustrated, like, are you like visibly angry and upset and, you know, getting kind of heated, or do you take it in stride and keep an upbeat attitude? So those are the sort of things that companies are looking for when you're doing these technical interviews. Oops. So how this series will help is that this is going to give you the space to practice these algorithmic challenges in a way that's, you know, a little bit more safe. You know, we're not putting a lot of pressure on you. There's no high stakes here, and a little bit more collaborative. So you're going to be solving challenges with, you know, the help of your team, and that's going to help you, you know, get into the rhythm of interview preparation. And as you can see, this is a lecture, also teaching you some patterns, some data structures that will help you solve these problems in a more efficient manner. Okay, cool. Let's get started. So, hash maps. Do you see my next screen? Because I don't. Let's see. Oh, here we go. Okay, cool. So hash maps. What are hash maps? So hash maps are a built-in data structure, and what they do is that they map keys, specific keys, to different values. Each key in the hash map is unique, meaning you can't have the same key mapping to different values. You have one key, and then it goes to a certain value. So the way I like to also think of it is like a file cabinet or like a bucket. Let's say you have buckets. You have an identifier, which is your key, that stores a value. And really, we use key value pairs all the time. Like, you can think of just anything in life and it has a key value pair. So for instance, if you want to read a book, the title of the book is a key, and the content of that book is the value. So if you're looking for a book and you pick up The Hunger Games, a key, you know you're going to read the contents of the Hunger Games. You're not going to read The Fault in Our Stars. It has a specific unique key that points to a value. Mind you, you can have different keys that map to the same values. That's fine, but each key itself has to be unique. Another way to look at it is I have this chessboard here. So each row and each column is identified by a unique key. So when I say A1, you know I'm talking about the black rook. You know I'm not talking about the white knight or the white pawn or one of the white pawns. I'm talking about a specific bucket on that chessboard. And this little photo down here is just a little bit of what a hash map would look like when you print it out. So it's basically this, this structure within the squiggly brackets here. So you've got your keys and you've got your values. Pretty simple, very easy to use, which is why I love them. Okay, so why would you ever need to use a hash map? Well, hash maps are great for a couple things. First, if you need to aggregate values for whatever reason, hash maps are great for them. An example of that is if you need to count all the characters in a string. Oh, my dog is coughing over here. Sorry. If you need to count characters in a string and you need to store that for whatever reason, a hash map is a great way to do that. If you have a graph and you want to store all of the neighbors of a specific node, a hash map is also a great way to do that. So if you need to map, values to a key, perfect use case for that. Also, storing answers for repeated problems. And that is just a roundabout way to say dynamic programming, which is something we're not going to go into because it's a more complex topic. That's something we're going to talk about at a much further date. But if you ever learn about dynamic programming, or if you've ever learned dynamic programming before, everyone always starts with a Fibonacci sequence because it's a very famous problem. And the Fibonacci sequence is each term in the Fibonacci sequence can be calculated by the prior two terms. So if you want to calculate the fifth term in a Fibonacci sequence, you're going to do that by calculating the fourth term and then the third term and then adding those two together. Now, say you had a program that calculated the nth term of a Fibonacci sequence. Cool. You could spend time calculating over and over all of the little subproblems and then provide that number, but that's going to give you exponential time. It's going to be super time wasteful. But what you could do is you could store all of the previous problems in a hash map. So for instance, if you wanted to get the 100th term, as we discussed, calculating that you would need the 99th and the 98th term. Well, calculating the 99th term, you would need, once again, the 98th term and the 97th term. So instead of calculating all of it all together, you could just store the 97th term and the 98th term. And then when you're calculating the 100th term, you can borrow the 99th term's previous one that you've already calculated. And all of that is just to say, it's a great, if you have repeating subproblems, if you're calculating the same thing over and over again, just go ahead and store it in a hash map and just keep a cache of that. So once again, a little bit more complicated than what we're doing today, but in the future, we will build upon this later when we talk about dynamic programming. Okay, cool. So Hashmap implementation, it is a built-in data structure. So most object-oriented languages are going to have a way to do it using a library. So Java, you're going to use their util library, and you're going to create a hash map, and you're going to add each value to the hash map. That's how you create it in Java. In Python, you can do it a couple of ways. First, we don't really say, okay, you can say hash map in Python, but what it's called is a dictionary. And so you can create an empty dictionary like you would in Java, creating an empty hash map. And then you can add different values like you see here. So like right here, that's adding key as a key, and then value as a value is adding a key value pair to that dictionary. Or you can initialize a hash map with a set of existing keys and values, like so here. So 1, 2, and 3 are the keys, and then first, second, and third are the values. And then in JavaScript, even though I believe JavaScript is not an object-oriented language, you can still create a hash map using the map function. So you can create an empty hash map and add them there, or add each key value pair to that hash map. Or like Python, you can initialize a hash map using existing key value pairs. All right. So how do hash maps work? So by the way, you're never going to have to like implement a hash map like from scratch, but it's a good idea to just know a little bit about how they work. And that's going to help you understand certain things about the functionality of hash maps like runtime. Okay, so first you have your key, and your key is placed into a hash function. And that hash function then produces a hash code, which is assigned to a bucket. And then once you find the hash code, then you store that value into that bucket. So you've got your key, you've got Lisa Smith, and you put it into the hash map. The hash map takes Lisa Smith, uses the hash function, produces a hash code, and then it puts it into the corresponding bucket. So if you want to store Lisa Smith's number, it's going to put it into hash code, index 01, and that's where you can find Lisa Smith's number. Now, hash maps aren't always clean, and how good or bad, a hash map is really depends on that hash function. Now, if you have a great hash function, that means you're going to have a really even distribution of hash codes, and you're never going to get a collision. Or by never, I mean rarely. And by a collision, I mean sometimes you have a hash function that takes two separate keys and maps to the same index. And what that does is that it makes it a little bit more confusing, because you have multiple values for one hash code. So there's different ways that hash functions or hash maps address this, but the most common way is that they use a linked list. So what happens is, like, say you have John Smith, and it goes to the bucket number 152, and you have Sandra D, which also goes to the bucket number 152. So what's going to happen in this case is that there's going to be a linked list, and so you're going to go through all of those values to find the key value pair that you're looking for. So typically now, if it's a great hash map, it's going to look like this, and so it's going to be at best case constant. It's just looking for the value. Here's the bucket, boom. But if you have a bad hash map, or if you have a bad hash function and you have a lot of collisions, then you can get all the way up to linear time, because sure, getting to the hash function or getting to the hash code takes constant time, but iterating through that linked list to find the specific key value pair that you're looking for is going to take O(n) time. So, but when you're doing these technical interviews and you're using built-in hash map features, you can assume that collisions are going to be rare, and on average, you're going to get constant time. So I wouldn't really worry about that. It might be something that you might mention, like, oh, on average, we're going to get constant time just because there could be collisions. But I wouldn't worry about it too much. Assume that the built-in function is going to produce the best efficiency, and just maybe might be a side note that you talk about when you're explaining the runtime with your interviewer. And by the way, if you have no idea what I'm talking about when I'm saying runtime or complexity, space complexity, yada, 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 we have a whole like recorded lecture series where in one of the lectures we do explain the concept of big O and space and time complexity. And I do recommend watching that if you haven't already, or if you're not really familiar with these concepts, as they're a very important part of the technical interview process. Okay, cool. So Hashmap runtimes. So thank you. So the best runtime that you're going to get is constant, as we talked about. Great hash function, even distribution of hash codes, very rare collisions. And so that's going to be constant time. At worst, terrible hash function, lots of collisions going through each linked list. At worst, you're going to get ON or linear time. All right, let's see an example. So to sum, I love this problem. Given an array of integers num and a target and an integer target, okay, cool. Return the indices of the two numbers such that they add up to the target. You can assume that there's a solution. You can assume that there's only one solution, and you are only going to use the same element once. You're not going to use it twice. And you can return the answer in any order. Okay, so an example of this, we have 2, 7, 11, 15, and a target is 9. So we would output 0, 1 because 2 and 7 equal 9. Example 2, we've got 3, 2, 4, the target is 6. In this case, we would output the indices 1 and 2. And then finally, we have 3, 3, we would output 0, 1. Okay, whoa, oh, I was supposed to alert myself that I was going to switch to my iPad. That's okay. So I'm going to do a new share here, and I'm going to go through my iPad. Whoops. Whoops. Okay, cool. So you can unmute yourself, just be aware that we are recording, or you can put it in the chat. Oof. Okay, Sneha, I saw your question. Can you explain why it is not considered an object-oriented programming language, JavaScript? For the sake of this lecture, I cannot. But I'm going to go ahead and after this lecture, probably link something to you. It's where it could explain the differences between JavaScript and object-oriented languages like C, C++, Java, Python, etc. JavaScript is special, but we'll take that offline. Okay, cool. So you can mention in the chat, or I feel like Michi is typing. She might explain it to you. Okay, so you can type in the chat, or you can unmute yourself. Just be aware of the recording. So remember the objective of this problem. We want to find the indices where the integers add up to the target. Can you think of a way that we could use a hash map to solve this problem? Any ideas? I'm going to tell you eventually, but I love to hear just any guesses. Now remember, hash maps are great for storing information. You have a key, storing a value. What would be a great bit of information you could store for later?
Yeah, actually, I've already solved this problem. So, I mean, can I still go ahead and answer? Yeah.
Yeah, go ahead.
Yeah. So basically, what it would do is take an element and the target and find the complement. What's the difference? And once we enter the entire array into the hash map, basically we'll be looking out for what's the number that would negate and give me the target. Like I'll find the complement in the hash map and try to get the result. So it's just O of n, and I have to just traverse through every element just once and get it out.
Yeah.
Is that right?
That is 1000% correct. So basically just summarizing what Ashika is saying here is the thing about, summing numbers together is that, if you have a number like 9 and you want to see if two numbers add up to it, so we have 9. Well, if you have a number 2, what number do you need to get to 9? Anyone tell me in the chat or unmute yourself.
7.
Exactly, right? You need 7. There's no, you're not going to get a 6 and a 2. Like, there's only 2 numbers. You're not going to get a 6 and a 2 and a 1. Like, you only need 7. If you have the number, 12 and you have the number 5, what number do you need to get to 12? It's not a trick question, I promise. You can tell me in the chat or you can unmute yourself. Perfect. Thank you. So what we can do, like Ashika was saying, is we can store where each number is, right? Because we want to return the basically the index of where the numbers are. So as we go through this array, we can store, let's see, I'm going to say locations, right? This is my hash map. So we can store the location of these values. And if we find the corresponding value, so like Ashika said, we have our target, which equals 9. And if we're at 7 and we want to know if 2 is there, just look for 2. And then that's going to give us where the location is. So that way we would just return 0, 1. Likewise, if we're here and we're looking for 6, we have our locations. So we have, 3 is at 0. Well, 3, we would need to have another 3, right? Now we're at 2 and we're going to put 1 here. And now we're at 4 and we can ask ourselves, we would need a 2. Is there a 2 in this hash map? Yes, there is, and the location is 1. Perfect. We'll return 1, 2. Same things here. Locations. We're at a 3. Is there a 3 here? No, because it's empty. That's fine. We'll just put 3 here, 0. We're at 3 now again. Is there a 3 here? Yeah, there is. It's at location 0. So we return 0, 1. So that's just a quick way of how you could use hash maps to store bits of information to help you solve the answer more efficiently. Okay, let's keep going. So now we're going to talk about heaps. Not my favorite data structure just because I don't really use it that often, but every now and then you're going to get something like top K frequent words, or top something where you're going to need, let me not get ahead of myself, but you're going to need the most frequent values or the least frequent values. And that's where heaps come into play. So what are heaps? So heaps are a specific type of binary tree. And apologies to people who aren't really familiar with what binary trees are. It's not something that we've covered yet, but it's something that we're going to cover in the future. Just for now, just bear with me. Okay, so heaps are a specific type of binary tree. First, they're full, meaning that before you start a new level, each node has to have 2 children. And then also they're organized by whether they're a min heap or a max heap. So if they're a min heap, the root has the smallest value, and all of the nodes are smaller than either of their children. And in a max heap, it's the same thing, but reversed. The root node is the largest value in the tree, and all of the nodes are larger than either of their children. So like I said before, if you have a problem that's like, give me the top K most frequent items, that is a heap. Anything where, and if you don't have to care, like if you don't need any other operations, besides just giving you the most frequent or least frequent items, you're going to use a heap. Okay, so heaps, the way that they work, like I said, they're trees. But how you keep a heap in place is that, or the organization of a heap in place, is that when you add a new node, what happens is that they bubble up until they're in the right spot. The same thing happens for deletion, except they bubble down. So if you have a min heap and a new node, you insert a new node and it's smaller than all the nodes or any of the nodes, then it bubbles up, meaning it swaps places until it's at the right spot where it's smaller than both of their children. And vice versa for a max heap. If you're inserting a new node and it's larger than anything else, it bubbles up or keeps swapping until it's in the right spot. Now, I just did a lot of words. So what I'm going to do here is I'm going to do a new share where I'm going to show you graphically. So that makes far more sense than what my mouth is saying. Okay, so I should have had a tree here. Oh, well. 8, 7, 6, 5. Three. I'm not doing this right, but it's because I'm doing 8, 6, 7, 5, 3, 0, 9. If you have no idea what I'm saying, and we're gonna stop at O. Okay, cool. What kind of heap is this? If I drew it correctly, what kind of heap is this? You can tell me in the chat, or you can unmute yourself. Max, how do you know? And if I did it correctly, I think I did. So the root is larger than its children. Perfect, thank you. Awesome. So now what we're going to do is we're going to add 9 to this. You know what? Let's make this a different color so that you know exactly what I'm doing here. We're going to make it this color. Good enough. Okay, so we're going to add 9 to this tree. But right now it's breaking the organization of the heap. So what we're going to do is we're going to bubble up or swap until it's in the right spot. So we're going to take that here and it's going to swap with its parent. And it's larger, so it's going to it's going to swap with its parent until it's larger. And once it's done and everything is in place, then your max heap is done bubbling up. When you delete a node, it's similar. So when you delete a node, you're always going to delete from the root. The root is always going to be the largest or smallest, depending on if you're talking about a max heap or a min heap. So when you delete a node, and let me go ahead and change this color to make it pink. So when a node is deleted from a heap, it's always deleted from the root. So that's going away. And what you're going to do, not what you're going to do, what the heap is going to do, is it's going to swap it with its rightmost child. And so what it's going to do is instead of bubbling up, it's actually going to bubble down, which means it's going to swap with the largest of its children until it's in the right spot. Cool. And that's how it works. Both with a max heap or a min heap, it's the same process either way. It's just vice versa. Okay, so even though heaps are binary trees, we actually don't represent them using a binary tree. We actually represent them using an array. And once again, I understand if you're not familiar with binary trees and it's not something that we talked about before, just bear with me. Just bear with me. In a tree, each insertion takes O log n time, because it's the height of the tree. And that's, roughly log n. Now, when you're building a heap, you have n you have n values, right? That's the size of whatever the number of items that you have. And when you're building that heap, each insertion is going to take log n time, and you're doing that n times. So building a heap, if you're creating a tree, is going to take O(n) log n time, which is pretty expensive when you're talking about just building a basic data structure. O(n) log n just to build a heap is like crazy. But there's some cool things about heaps that make it the perfect candidate for array representation. One, we know that heaps are going to be full, which means that before we add a new level, all of the nodes are going to have 2 children. So there's not going to be any gaps. Second, we know that the largest value and the smallest value, or the smallest value, is going to be the first spot in the array, or the first spot in the tree. So if we're using an array, we can just go ahead and like put it into the first spot, index 0, and then just go ahead and calculate where the children are going to be. And the way that we do that is through these calculations. Well, the way that the API does it. I am not going to advocate you doing this from scratch. It's good to know, but don't build a heap from scratch. But the way that the API does it is that it inserts the first position, and then it calculates the children, all the subsequent children of the tree, and it does that n times. And so instead of doing O(n) log n, making that complex tree, what you have is just an array with n insertions. So we're actually reducing the time from O(n) log n to O(n), which is pretty great in terms of efficiency. Okay, so you can also, another great thing about that is that when you heapify an array, it does it in place too. So you're not creating a new data structure, it just takes the same array and it sorts it in a way that is, turns it into a heap, but it does it in O(n) time. Okay, cool. So if you're using Java, that means you're going to use the util library, and you're going to use a priority queue. That's what Java calls its min heaps. And if you're going to use a max heap, you're going to use the util library once again, but you're going to use what's called a reverse order collection. If you're using, hello. Okay, here we go. If you're using Python, you're going to use a min heap, built-in min heap, and you're just going to heapify an array. And they don't have really a max heap, but what I use when I'm using Python's heapify structure is that you're going to basically use the negative of those numbers, and that essentially gives you the same thing, because you have the negative, the most negative number, the absolute value of that is going to be the largest number. So it's basically essentially a max heap. It's, a different way to get to the same thing. If you're using JavaScript, I am sorry to say that there is not a built-in data structure, to my knowledge, that creates a heap. So in that situation, I would just do the roundabout way of doing it. And I'll talk about that more when we're doing our example problem here. But I would do the roundabout way of doing, solving the problem. But maybe I would mention something like, if I were using a more object-oriented language like Java or Python or C++, I would heapify this. So that would take my runtime from O(n) log n to O of n when creating this heap. So I know there's a lot of people in here that use JavaScript, but to my knowledge, a heap is not a built-in data structure. Okay, so runtimes. We're looking at O(1) constant time to look up just the min or max value, constant time because it's the root. Inserting it is O log n, inserting any values, and deleting it, any value, is O log n. And to build a heap or heapify is linear time, as we discussed. All right, all right, all right. Oh my goodness, what is going? My slides are a little funky here. Okay, so let's see an example. Top K frequent words. Very popular example. If you're being asked a heap question in an interview. So given an array of strings, words, and an integer k, return the k most frequent strings. Return the answer sorted by the frequency from highest to lowest. Sort the words with the same frequency by their lexicographical order. Okay, what the heck does that even mean? So in this problem, you're going to be given an array of words. And your job is to return the top k most frequent words. Now, if you have two values or two keys that have the same values, you need to return them in lexicographical order, meaning alphabetical order. So if you have, for example, here, we have an array of words. I love LeetCode. I love coding. Obviously, I got this from LeetCode. And you're going to return the two most frequent words here. In that case, it would be I and love. But I comes before love or L in the alphabet, so you will return I, comma, love. In this one, we have the day is sunny, the sunny is, and you're going to turn the top four frequent words. Even though that is sunny are the four most frequent words, you're going to return them. Wait, what? Oh, sorry, they're not. No, they're not. There's way more of those than everything else. Okay, so you're going to return the first because it's the most frequent word. Then you're going to return is because it's the second, and then sunny, and then day. So there you go. There's four words here, and it's the four most frequent, so you're going to return all of them. Okay, cool. So usually I like to tell you or ask you what's the best way to do this. I mean, we've got some time left. I can ask you. This is more of a medium problem than an easy one. So like, no worries if you don't. I actually had to be taught this problem before I knew how to do it. But can anyone think of how you would solve this using a heap? I'm gonna take like a minute.
I actually have a question. So
Yeah.
let's say the first thing when I saw while asking for, the frequent words, I thought, why can't we use a hash map? Because it also does the same. Then we retrieve the max out of it, right? Like in the order. Is
Yeah,
is it
that is a
not a
great question. I love that question. You know what, Ashika? I'm going to answer a question by let's just go ahead and solve this. And hopefully I
Sure.
will answer a question.
Sure.
So, cool. Let's see, what was it? I love LeetCoding. I love LeetCode. I love coding, I think is what it was. Okay, let's pretend that these have quotations over it. These are all strings. So I love LeetCode. I love coding. Those are our words, and our target, I believe, was 2. Okay, cool. So Ashika, what she asked was, why can't I just use a hash map and then sort and return the max values, right? Is that what your question was, Ashika?
Yes, yes, that's right.
Perfect. So we have 3 parts of this question. So first, we need to know what the count is for each word, right? So first, we need to know what the count is for each word. Then we need to get the top K elements. So first, we need to know what the count is, right? Which means that we need to have some sort of structure that tells us how many occurrences each word has. Well, what data structure is the best one for doing this? It's not a trick question, Ashika, you already told me.
Hash map? Is it?
Exactly. We just went over
Okay.
it.
Oh,
Anytime you want to map, anytime you want to map keys to values, a hash map is going to be your perfect way of doing that. So yes, you're absolutely right. So we're going to
got
start with like frequency, and we're going to have I, which is going to be 2, love, which is going to be 2, LeetCode, which is going to be 1, and coding, which is going to be 1. I'm sorry, I should have attempted to make my handwriting better. Oops, just listen to my words. Okay, so you're absolutely correct. We're going to start with a hash map because that's what's going to give us, we need to know how many times the words are there. Like we have to use a hash map at that point. But then the interesting thing that you said was sorting. And Ashika, what is a typical runtime for sorting?
login if it's binary. I mean,
Not login.
okay.
For sorting and then
Mm.
yes, yeah. So because you're doing it n times, you're doing the sort and you're sorting n elements. So a typical sorting algorithm is O n log n time. Now, what do we know about heaps? What is the runtime of heapifying an array?
It's in.
Exactly. It is O n time to heapify. So to answer your question, can we just do a hash map and then take that and then, excuse me, sort it and return the max ones? Absolutely, we totally can. And that's going to give us a runtime of O n log n. But we can increase our efficiency even further if instead of sorting our array, we heapify it. So that's pretty much what we're going to do here. I mean, I don't even know if like what to explain further because I kind of just explained it, but like let's go over it again. I'm going to say the same words again, just in case. So you're going to take your count, just like you said, Ashika. We're going to take our count, or we're going to count the frequency of each word using a hash map. So boom. Then what we're going to do is we're going to grab, oh no, there's a little bit more that we need to know here. So what we're going to do is we're going to grab the keys and we're going to grab the values. So we're going to, because we need a way of having, if we're going to heapify, we need an array to heapify, right? We can't just heapify a hash map. That's not going to work. So we need to go through and grab the key value pairs. So what we're going to do is we're going to take, I probably should have made this a lot more neat. I'm so sorry, everyone. I'm just sort of writing here. Okay, so we're going to take, so we're going to say, like, let's say we had this and it was our frequency, right? And that was a hash map. Then we want some sort of array. Let's say that it's word count. And what we're going to do is we're going to go through this hash map, collect the key values, and put them into an array. So we're going to have something like, and let's do like a set here. We're going to have I, comma, whoops. We're going to start first with the count because that's what we care about first. Because we need it to be in order of count. So we're going to have 2, comma I. We're going to have 2, comma love. We're going to have 1, comma LeetCode. And we're going to have 1 coding. Now I use Python. If you're using Java, you can just use reverse order collections. I use Python, so I would actually put these as negative to make it a max heap because we want the top, meaning the largest k elements. So now we have this array, which is word count, right? And the next thing we need to know is how can we put it in a way that we are getting the topmost values? And to do that, we'll just heapify it. And what it will do is that it will in place organize this so that it will have the it will create a base. It will organize it in a way that's a heap. And so what we can do here is heapify this, and then for each, so for I until k, whatever k is, in this case it's 2, we're just going to take our new heap and we're going to, I'm not sure what the term is for Java, but in Python we just pop the heap. So we're going to pop it until we reach k. And that's going to give us our, and then maybe we'll have like a result. So like we'll have like a results array for I to k. We're going to pop the heap and append to the results. This is so messy, I apologize. I should have figured out a game plan of writing this before I just started writing. Okay, so what did I just say? We're going to count the frequency of the words and we're going to map it to the keys, right? And so that's what we did here. We mapped the frequency to keys, just like Ashika said. Then what we're going to do is we're going to collect those values and put it into an array. Because in order to heapify, you have to have an array first. Cool. Once we have that heapified, we're going to grab those top k values and add it to our results and then return that. Now, a common question when doing top k elements is, wait, what about the sorting? Don't you have to have it in a specific order? Like what if in here, I just happen to come before love, but what if, love came before I? Well, the cool thing about heaps is when you're building or when you're heapifying an array, what it's going to do is if 2 keys map to the same value, so let's see, I'm going to use a different color here. If 2 keys map to the same value, so if -2, excuse me, if 2 elements have the same amount, it's then going to sort with that second value. So it's going to be in order. So it's still going to maintain that O in time. And that's how you solve the top k frequent. Anyways, that's how you solve that problem. I got to go back on my notes to see what the name of that problem is. Layla asks, can you explain the heaping process a little more? I sure can. Can you elaborate a little bit more about what exactly you want me to explain? We actually have a couple of minutes left before I usually go overtime, so we have a couple of minutes left here.
Just kind of wondering about the, I guess that is like a sorting process, right? In the array. So do you know what kind of sort is actually going on when it does the heapify of the array?
Yeah, so let me go ahead and go to the slides here. So it's top k frequent. I don't know, I can't speak English. Okay, so remember what we said about like a binary tree and how we don't store trees. We don't actually store heaps in binary trees because that would take O(n) log n time. And instead we heapify arrays. So it's basically that process. So what happens is that we take the array. So we know a couple of things. We know that a heap is going to be full, meaning each node has 2 children before we add a new level. So there's not going to be any gaps. We also know that the root is going to have either the largest or the smallest value. So because we know that, we can create a heap using an array by just inserting the largest or smallest value at that first position, and then calculating the positions of all the other elements using these calculations here. So for a parent, it's current index -1, divided by 2 to find something's parent. To find the left child, its current index times 2 plus 1. And to find the right child, its current index times 2 plus 2. So it does those calculations n times, and that's how it organizes an array into a heap. So it basically repositions them and does n insertions into the heap. You are never going to do that like yourself. You're not going to do that from scratch. But the API, or the library that you're using, whether you're using Python or Java or C++, whatever, any of those, that library, that's what it's doing under the hood. And that's why it's O(n) time, because it's just a series of calculations. Does that make more sense?
Yeah, it does. So basically, it's if you are given like a bunch of numbers, and then basically it's going to go through all of those numbers and find the largest number, and then placed at the beginning of the array, and then do calculations based on that number to find the placement of the other numbers.
Correct. And it's going to do it in linear time. So heapifying, no matter like how unorganized or whatever your array is, heapifying is going to do it in O(n) time.
Got it. Thank you.
Yeah, for sure. So that is the basics of min-max heaps. Like I said, it's not something, honestly, in my I've been doing technical interviews now for like a couple of years now. I mean, that's not like forever, but I've been doing quite a few technical interviews, and honestly, heaps haven't come up for me personally. But they're good to know. They're good to practice because you never know. And if you are doing something like top K frequent words, it will reduce that runtime from O(n) log n to O(n), because Ashika's right. You can totally just use a hash map to store the values or to store the count, and then sort them and then just return that. But that's going to give you O(n) log n. And if you use a heap, or if you heapify your array, it will take that O(n) log n down to O(n) runtime. Hash maps, however, I use so often. Like it's like probably like every other technical interview, I'm using some sort of hash map because it's a really great way to store information, especially because to be honest, a lot of problems that I see are like string and array problems. And hash map is a great way to, if you need to have a count for any reason, a hash map is a great way to go through that. Okay, so that being said, let's go ahead and practice. So miraculously, I did not go way over time here. So I'm going to give you, I'm going to give you about 40 minutes to do this problem. That's like a Christmas miracle here. So I'm going to explain the problem, and then you can ask me any questions, any clarifying questions. And then we're going to break you up and you're into different teams, and you're going to just practice. And like, I purposely give you more challenging problems because I want you to try to be a little creative in how you come up with questions, but like, don't sweat. Like if you're not, if you don't like come up with, code, working code in time, like don't sweat. I purposely do it so that you don't, because the goal here is to think creatively, to sort of think outside of the box and just play around a bit. And then, do it with the course of a team. So like, don't trip. A lot of these problems took me a while before I got to do them, like with, 30 minutes and under, but try to have fun while you're doing them. Okay, cool. So let's talk about the problem. Gosh, what is going on with my slides? All right. Longest substring with the same letters after replacement. So you're given a string with lowercase letters only, so you don't have to worry about caps. And you are allowed to replace no more than K letters with any letter. And then find, I said that all wrong because I can't read. So given a string with lowercase letters, if you're allowed to replace no more than k letters with any letter, find the length of the longest substring having the same letters after replacement. Okay, so what the heck did I just say? Because I'm really terrible at like reading, apparently. So you have a string like this one here, example 1, and you're allowed to do up to 2 replacements. So if you do 2 replacements or up to 2 replacements, what is the length of the longest string that you can create that's all the same characters? So in this first example, you're going to return 5 because you have B, C, C, B, B. C and C can be replaced to B, and you can have B, 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 which is 5 characters. Another example, we have example 2, a string A, B, B, C, B, and you can only make up to one replacement. So in this case, we would output 4 because we have B, B, C, B. We can just flip that C to a B, and the length of that substring will be 4. Last example here, we have A, B, C, C, D, E, and our output would be 1. And you can either flip the B to a C to have CCC, or you can flip the D to a C to have CCC. But either way, the longest substring is going to be 3. Any questions before you all practice? All right, so really quickly, here's what we're going to do. I'm just going to show you how we do this. All right, I'm going to stop the share and I'm going to reshare. Let's see, let me get out of this. Okay, cool. So this is how it's going to go. You're going to be broken up into different groups, and I'm going to post this. It's case sensitive, so just keep that in mind when you go to this address. And when you go to that address, it's going to take you to a list of whiteboards here. And so what you're going to do is you're going to open that, and you're going to, that's going to be your whiteboard. You know, this is where you're going to think. We have a little thing here that can help you, like, you know, think of ideas and how to implement that. And then once you're done, if you do get to the point where you have working code, no worries. If not, you're going to open a Replit. Hopefully you created an account already. And I recommend, so we're language agnostic here. So if you really love JavaScript, but everyone in your group does Java, no worries. I recommend one person being the driver of the code here. So they are the ones who write the code, and then everyone else tells them what to do based on the algorithmic steps that you've already created. So say this is like, reverse a string, and, I write in Python, but everyone else does Java. So everyone would tell me so what is the first step in reversing a string? So like create a start and end pointer. So I would be like, all right, cool. So start equals 0, and like, I don't know, end equals 0. Okay, what's the next step? Iterate through each character there. Okay, cool. So like while start is less than, so even though, they're not typing in my language, you can work together to create the algorithmic steps, and then your partners will just feed you each step while you type the code. If you want more than one person working on the same document, totally fine. Just go to that invite link, click it, generate a join link, and share it in the chat for your group. It looks like you're sharing it to the whole class here, but you're not. You're just sharing it to your group. So breakout rooms. Remember your breakout room, click the number of the board that's associated with your room. Use this to work out your problem. And then when you're ready, go ahead and use Replit to type up your code. And if there's no questions, brief pause. Then we'll go ahead and break you out for 40 minutes. Sorry, let's go. Okay, so let's now talk about how I would solve the problem, how I would approach the problem. So And once again, for everyone, if it's, we're over time, so if you need to leave, totally fine. But for those who are watching at home, here's how I would do it. So a simple way to do it is actually a combination of things we would do, a combination of techniques that we've used throughout the lecture series here. So I would use a combination of a sliding window and a hash map. So a hash map to use so a sliding window, if you remember from our first lecture series, the technique we used was the 2-pointer technique, which is also called the sliding window. So basically what you do, basically what you do is you use a sliding, or you have 2 pointers and you use them to iterate through your array. And you keep those pointers in place until a rule breaks. Like, for instance, you've ran out of replacements and you need to adjust for that rule breaking. Excuse me. So one thing we can do is we can use a sliding window to keep track of what that longest substring is. And then what we can also do is use a hash map to store the number of replacements made. And so, gosh, who was it that was talking? I forgot. Sorry, I forgot your name. But so an interesting thing was the person who talked about their solution. So using a hash map for locations, that is an interesting way, and I'd love to explore that. One way, though, to keep track of where things are is to just keep track of how many replacements each character has used. So, I've said a lot of words, which can seem kind of abstract. So what I'm actually going to do right now is I'm going to code this up. I was not prepared to do this, but let's just hope that I do it quickly and least embarrassing way. Okay, cool. So I'm going to just do this because these are going to be our test cases. Okay, so we've got example 1 and we've got example. Wait, is this it? No, this is totally not it. Wrong one. Okay, example 2, I guess. Example 3. And example 1. Okay, cool. So looking at this, I know that I need to iterate through this string. And the first thing I do, honestly, the first thing I do whenever I'm solving a problem is I think, can I use a sliding window for this? Okay, so what can I do for a sliding window? So I can have a pointer. I can have, let's say we have AAB, CC, BB. And we have our start. Actually, let's do this without that. I know it's not working here, but so we can have our start pointer and we can have our end pointer. And we want to test out having each string be the same letter. So maybe what we can do is have our start be the first letter. And then whenever we iterate through the string and we make a replacement, maybe we keep track of that, right? So let's make a replacement here. Okay, and somehow keep track of that. So now in replacements, let's say we had 2, maybe you have something like replacements left and we had 2. So now it's actually 1. Okay. So we keep going again. And we're looking at this first character here to see if this matches that, right? Because we're going to look to see if we can have all of this be the same letter. This isn't an A, so we're going to go ahead and make a replacement. So we have replacements are now 0. Okay, cool. Oh, and we also have to keep track. We have to keep track of what we're doing here. So to keep track, or to get the length, I know that the end character minus start is going to get me, let's see, 0, 1, 2, 3, 3 minus 2, it's going to get me that plus 1 because we're counting the characters. So we know that it's going to be n minus start plus 1. But in this case, we know that the max length right now, and we're going to, every time we do this, we're going to just recalculate the max length. And so right now we know it's going to be AA, BC, so it's going to be 4. Okay, cool. And our replacements left is 0. So now we go here, and C is here, and we need to make a replacement, but C, we don't have any replacements left. I'm familiar with sliding windows, so I know what I'm gonna do is I'm gonna break the rule, and I'm going to do, I'm going to change this to A. I'm not really changing it to A, but I'm just changing the replacement. I know the rule is broken, and so what I'm going to do is I'm going to keep moving, because this is a sliding window, right? So you change the pointers or the edges, boundaries of the window until the rule is no longer broken. Oh, no worries. Okay, cool. So here the rule is broken, right? We took one more replacement even though we didn't have room. So now we need to just keep, doing the window until the rule is broken. But I don't really know, like, how do I know where the replacements are? Like, how do I know what replacements, like, I need to know that sort of information. Like, in order to move the sliding window to a point where I know that the rule isn't broken anymore, I need to have a way of storing that information. And so what is a data structure that stores information very well, that maps values to a key? Hash maps, right? So one thing we can do is, let's see. So I can say something like replacements. I can like have this dictionary. I'm using Python, we're using a dictionary. So I can use this dictionary, and every time I make a replacement, instead of keeping track of the location, I think what I will do is I will just keep track of where I made the replacement. So instead of keeping track of like 0, 1, 2, 2 here, I'm actually going to say that I did a replacement at 0, 1, 2. Just kidding. I did. Okay, sorry. For the character B, I did 1 replacement. And then for the character C, I did 2 replacements. So the number of replacements, or the replacements left, because I don't want to go ahead and calculate the total. That's going to take O(n) times. So I'd rather just have like this variable that keeps track of how many replacements are left. So here, so instead of like doing that, well, for visual reasons, I'll just keep that. Okay, so here I can go ahead and keep track of the replacements. So B has 1 replacement and C has 2. Okay, cool. And what I can do here with my sliding window, we know that using the last C here, that breaks the rule, right? Replacements left is -1. You can use 2, but you can't use more than 2. So what I can do is, I know then this is done. A string starting with the character A, it's done. The max we can get is 4 2 replacements. Okay, cool. Well, how about this character here? Well, we'll keep checking by moving our sliding window. And if the replacements left, if it goes back to 0, which means we use a max of 2 replacements, then we know that we can, count that as a valid response. So we can't use AA, B, C. We can't do that because that's too much. So we're going to go ahead and move this 1 over. So what I can do to sort of, fix my broken rule here is anytime I'm moving the sliding window and I'm moving the start character, if that character is in the replacements, like we're using the start character as the character that we're using for the longest substring, right? If it's in here, then that means we're starting with that character. So we're not using it as a replacement. So we can actually just get that out of the dictionary, set that value to 0, and then take that value and add it back to the replacements left. So I'm going to keep doing this in letters, and hopefully that makes sense. So A is not in replacements. We didn't replace A. So we're just going to keep moving because replacements left is -1. We're at B. So now we're going to look at a new string starting with B. B is in replacements, but if we're looking at a new string starting with B, we don't need to use that replacement. So what we're going to do is we're going to add 1 back to replacements left. So now it's going to be 0, and we're going to set this to 0 because we have a new string starting at B and ending at C. And C has 2 replacements because C doesn't equal B. So even though it took 2 replacements to switch C to A, it's also going to take 2 replacements to switch C to B. If it didn't take 2 replacements, then that would mean that C was B, and then we would have cleared that out. So now instead of A, now we have B, B, B. And so, you know, end minus start. So 0, 1, 2, 0, 1, 2, 3, 4, right? Is that 4? 5? 5 minus, I can't count. 0, 1, 2, 3, 0, 1, 2, 3, 4. 4 minus 2 is 2, plus 1 is 3. So we know that this is 3 characters. Okay, cool. Let's keep going. So E, it matches B, so we know we don't need to replace it. And now, but the max length is still 4. And then now it matches B, so we don't need to replace it, but the max length now is 5. Okay, cool. So that's kind of the algorithm we can use to solve this. But I did promise code. So let me go ahead and put it up. So let's just recap what we're going to do here. Whoops. Use a sliding window to iterate through characters. If the end car doesn't match start car, then replace it, right? And by replace it, I mean, add to replacements hash map and subtract replacements left. Okay, but if it goes negative, so if it goes negative, then if negative, keep repairing. And by repairing, I mean, let's actually flesh it out later. Keep repairing until until replacements is greater than or equal to 0. Okay, what the heck do we mean by repairing? If start car is in replacements, set to 0, and then add value back to replacements left. Okay, cool. Let's go ahead and code this up. So I've got my solution in the class solution. Once again, I type in Python. So I'm going to try to speak it out. You know, apologies if you're not familiar, but I'm going to try to do my best to communicate what I'm doing. Okay, so we're going to get a string. So def, I don't know, what is this? Replacements. Length K replacements, something like that. Okay, so we're going to get a string. So S, I'll just say string to make it easier. String, and that's going to be a string. And we're going to get a K, which is going to be an integer, and we're going to return an integer. Okay, cool. So here's our pseudocode, our algorithm. I'm going to do it here. No, no. Okay. And when you're in a technical interview, I really recommend pseudocoding before you write any sort of code. Get your algorithm together before you really spend a lot of time thinking about your algorithm, and then get your code together or your pseudocode together, and then code. Like coding should be the last thing that you do, because you never want to start coding and then realize you have no idea what you're doing, and then have to start over in the middle of a technical interview. That has happened to me plenty of times. It does not feel good. Also, another thing that you should do in a technical interview, especially if you are doing this live, you want to kind of analyze what you're doing before you do it. So let's just do this right now. What would be the runtime of doing this? So iterating through the array, at most, you're going to iterate it through it twice. You're going to iterate it once through with the end pointer, and then another time with the S pointer. And so what is that runtime if you're going through each character at most twice? What is the time complexity of that? Anyone? Oh, so shy in here. All right, I'll tell you. If you're iterating through each character of a string, that's going to be linear. Oh, what do you know? In the 9th hour, Ashika, yes, you're absolutely correct. It's going to be linear time, because you're iterating through each character. As n gets larger, the number of visits that you have to do for each character grows in direct proportion to that size. Changing this, here and there, that's going to be constant time. Same with that. Adding replacements is going to be constant time. So in all, it's going to be ON time. Space time. Does anyone know what the space complexity would be with this? As the input size grows, as there's more letters, how much space are we going to use? And really the most space that we're going to use here is this hash map here. Any idea? So Sneha said linear time, which at first glance would seem to be the case. But the interesting thing is with letters, a cool little trick that you can use whenever you're doing your technical interviews, with letters, the most letters you'll have slots for. Like say we put every single character in the alphabet here. How many characters is that? Like how many slots is that? How many key value pairs is that going to be? Anyone? I'll go ahead and tell you. It's going to be max 26 characters, right? I think that's it. 26, 27, one of those. So it's going to be a maximum of 26 or 27 characters because we're only using the alphabet here. So we know if there's only going to be 27 slots, 26, depending on if I know the English language. If there's only going to be a max of 26 characters, no matter how big or how small your input size in, maximum it's going to be 26 characters. So that is constant space complexity because it stays the same regardless of the input size. So that is just a little quick analysis. I'm okay with ON time complexity because you're going to have to iterate through the characters. That's just how it is. And I'm definitely cool with constant space complexity. So let's keep going. So we're going to use a sliding window to iterate through each character. If the end doesn't match the start, replace it. Okay, cool. So I'm going to say end. Let's see. I'm going to say start. I'm going to have a start pointer, which starts at the first index. I'm also going to have length. I'm going to say max length to be specific equals 0. We're going to go ahead and initialize that. And anything else? Oh, we have to have a dictionary. So, and replacements. So replacements left equals K, I'm going to say. And then we're going to have a dictionary. So replacements, that's going to track all of the replacements that we made. Okay, cool. So now what I'm going to do is we're going to go through the sizing window. So for end in range len of string, and what that does is we know we're going to use a for loop because we know we're going to iterate through each character. So 0, 1, 2, 3, all the way to the end. So if the end card doesn't match the start card, replace it. Okay, so if end, oops, if string end does not equal string start, then replace it, which means replacements. Ooh, does that spell replacements? Okay, cool. I think it does. Replacements string end. You know what I'm going to do? I'm actually going to use a default dict, which is a Python collection from collections, import default dict. Basically what it does is instead of me having to check every time if something is in the dictionary, it's going to go ahead and just initialize it to 0. So that's just going to be useful for me. So instead of, so I'm just going to say replacement string end, instead of saying like equals 1, if it's, you know, the first one and the or plus equal 1, if it's like, you know, subsequent ones, I'm just going to say plus equal 1. So it's going to initialize it to 0 and then it's going to add 1. Okay, and then we're going to do replacements left minus equal 1. I feel like there might be a more efficient way to do this, but for the sake of time, I'm just going to keep doing this. Okay, cool. But what happens if replacements, if we go beyond what we have? So if we do go beyond what we have, then keep repairing until replacements left is greater than or equal to 0. So let's say like while replacements left is less than 0, we're going to repair. So we're going to move that up. So start plus equal 1. And then we're going to say if start cart is in replacement, set to 0. Well, first I'm going to actually add the value back so that I have the number, I have the value. So replacements left plus equal replacements string. Sorry, I was thinking about something. Start. Okay, so if it's not in the dictionary, so like we're not going to put something, there's not going to be a value for A just because it wasn't replaced. But what this will do, this default dict here, it's going to initialize it to 0. And if it is 0, that's fine. We're just going to add 0 to replacements left. So start plus equal 1, move the pointer forward, add this to replacements left, and then replacements string start equals 0. So in this case of A, since it's already 0, like that's not going to do anything. But if we have something like B, where it's the start character and it is in replacements, we're going to add the number to replacements left. So in here, it would have been like 1. So we would have went from -1 to 0. And then we would have changed replacements to 0. Okay, cool. So once it's doing that, we're going to do that. Oh, and the last thing is once that's all done, we also want to make sure that we're getting that max length. So I think max length. So max length is going to be the maximum of max length and also n minus start plus 1. Okay, cool. And then once that's all done, we're going to return max length. Okay, cool. So I'm not going to evaluate just because we kind of did a pre-evaluation before this to see if this works. But we are going to check that it does indeed work because I could have messed something up really quick. So solution equals solution. I'm going to say string comma k equals, let's just do this real quick. Ugh, I hope this works. Otherwise, it's going to be really annoying to debug this. Okay, cool. So we're going to print expected equals what? Equals 5. And then actual is, and then solution dot, thank you, string k. And I'm going to do that one more time. And one more time. Okay, so we're going to do this, and it's going to be, ooh, I think this is 1. This is 1. Oh, hex now. Okay, cool. And then that is going to be example 3. And it's going to be, oops, oh my God. Okay, it's not going to be, wait, what is expected here? 4 and 3. Okay. 4 and 3. All right, let's see where I made typos. Oh. Okay, it's recorded. We'll say goodbye to this. All right, oh yeah, self. Now let's forget that. Okay, let's try that one time. Key error B. Line 57. Did I do something here? Line 57. Oh, wait, what? Key error B. Line 42. Okay, gotcha. So for end, if the string end character does not equal the start character, then add to replacements. Wait, first of all, oh God, did I not do a default dict? I didn't even set this to a default dict. Wow. Okay, let's try that again. Type object is not subscriptable. String end, replacement string end plus equal 1. By the way, this is actually where you would evaluate. And so my decision to not evaluate means I have to go ahead and debug this, but let's go ahead and make sure that this is fine. My evaluation would have caught this, but I try to be quick about it, but obviously I made some typos. Okay, so replacement string end plus equal 1, type object is not subscriptable. This is in line 42. Okay, so if string end doesn't equal string start, we're going to add replacement string end plus equal 1. Type is not, what did I do? Oh, shoot, my bad. Gosh. You have to set what it is. Oh, gosh, I'm so embarrassed. Okay, cool. After all my typos are done. So, okay, so what I did there, whenever you set a default dictionary in Python, you have to say what kind of expected value you're going to get. But yay, it worked out. So the expected value was 5, we got 5, expected value is 4, we got 4, expected value is 3, we got 3. I can say with confidence that I think that this is the correct algorithm for the problem. And then we will be on our merry way. So that is how I would solve this problem here. And it's 12:35, which is way past time. Thank you so much for hanging out with me to go through the solution. But remember to practice, and I will see you in the new year, or I will see you in Slack, where I will be adding my like what I'm doing to study, because I'm always interview prepping. And I hope to see your answers in the Slack. So thanks for hanging out with me, everyone.